Alright, the next thing this is what we're going to spend the next 3 days really focusing on. So you can think of it over the next 3 days, Tuesday, Wednesday, Thursday, going towards the test on Friday, is going to be basically all right triangles and right triangle trigonometry. Today is kind of like your preview into the right triangle trig and everything that goes with it. And then we're going to see all sorts of application of it, not only just straightforward, just the math of it, but we're also going to see how it plays out in the real world. Because honestly, when you think of math, you think of, all right, what am I going to use in the real world? One is linear functions are a big deal. The linear relationship between two variables, big thing. Geometry, huge. And believe it or not, right triangle geometry is huge. Right triangle trig and right triangle geometry is absolutely enormous. So if we have the right triangle, what does this box represent? The 90-degree angle. Now, what would we call segment AB? Yep, that's our hypotenuse. This guy over here and this guy over here, this is a leg and this is a leg. Now, a lot of times what's going to happen is when you deal with angle A, the side opposite angle A is going to be referred to as A. I know it's very, very complicated, but a lowercase a for that. And the side opposite angle B, which is another one of your acute angles, that's going to be referred to as B. And what do you think the side opposite C is going to be referred to as? C. Now, what do you think the main thing of right triangles? What's the theorem that you're going to be dealing with the most as far as just the geometry part of it? Yes. Now, this is the Pythagorean theorem. Leg 1 squared plus leg 2 squared equals the hypotenuse squared. This guy we change usually to a squared. This guy we change usually to b squared. And this guy is c squared. So this a squared plus b squared equals c squared idea is something that just doesn't go away. Now, here's just an example of a straightforward Pythagorean theorem problem. A lot of times when you get a real life situation, story problem if you will, and it ends up being a right triangle that you're able to build, you should be happy because it's a right triangle. Right triangle is either going to lead you to trigonometry, which is a lot easier than you guys make it out to be. You guys like to make it harder than it is. It isn't that bad. You just got to remember a couple relationships and then you're good to go. or you have to use a Pythagorean theorem. Now, with this, if I know two sides and I need the third, guess what I'm going to use? Yep, I'm going to use the Pythagorean theorem. So, what's one of my legs? In the triangle, what's one of the legs? Is it the 4, the 7, or the x? Alright, 4. I'm going to take that guy and I'm going to square it. What's the other leg? And I'm going to square that, and that's equal to x, but I'm going to square that as well. Now, remember, going to have 4 squared and 7 squared, so we have to square this. What's 4 times 4? 16. What's 7 times 7? 49, and that's equal to x squared. Now, 16 plus 49, well, if that was 50, it would be 66, right? But it's 1 less than 50, so it would be 65. However you want to add them together, go right ahead. You know how everyone complains about the new math? People complain that sometimes kids are learning stuff with this new math. This whole idea that, alright, if I took 1 from 16 and put it over here and made this 50 and made that a 15, it's easier to add 50 than it is to add a 49. Because it's a multiple of 10. It's easy. 50 plus 15 is going to be 50 plus 10, which is 60, plus another 5, which is 65. It's a quick way of doing stuff. And it is what it is. I always say that the new math is just regular math, just taught in a different way. And it's just different. And so people always freak out about different stuff. Alright, do I want x squared or do I want x? I want x. So I need the square root of x squared, which would be equal to the square root of 65. Now, personally, it doesn't matter to me if you reduce it or not. However, I want you to get into the habit of reducing, or not reducing, but simplifying radicals. So take this 65 and think to yourself, can I break that up into 2 numbers? Okay. Since it's a 5, I know it's 5 times something, right? 5 times 13. Now, the question is, are there any perfect squares in there? Well, 5 is prime, 13 is prime. There's nothing there. X, we can leave it as a square root of 65. Now, one thing that I do not want you doing, I know there's always something, isn't there, that the teachers don't want you doing? Well, I can take my phone out because I'm the teacher. If you take your phone out, I'm taking it again. Alright, what I don't want you doing is this. Take it, I think, saying that the square root of 65 is approximately 8.06. I don't want you doing that because this is an approximation. This is an exact answer. And what you want to do is you want to keep your answers exact. So you don't want to get stuck into the whole approximating thing. Besides, if this is just one part of a problem, you want to keep this and use the square root of 65. You don't want to use 8.06 because, as you saw, this goes on forever and ever and ever. Well, if you only use 8.06 or 8.1, you're losing all those numbers. Your numbers are going to be off. And I like to use the whole, what if you're designing an airlock for a space station and you start rounding your numbers? Well, the airlock might not lock out all the air, or it might not lock in all the air, and then all of a sudden you're going to kill your astronauts, and you don't want to do that. No, that's a pretty gruesome way of thinking about it, but you don't want that to happen. Not on your watch.